I'm sorry I can't be there today. My daughter is sick and she got me sick, so we're both fighting off our fevers and virus. You do still have your quiz tomorrow. It is no calculator and there is no reassessment. And it is going to cover SLTs 4 through 7. So make sure to look at your calendar and figure out what exactly you are supposed to study tonight. We will pause the video here and give you 8 minutes to try the warm-up. Write these problems down. They are not in your packet, and then simplify. Okay, these should be the answers that you got, and I will go through how I got them. So for number 1, when you have a complex number squared, it means multiply by itself. So you can box method, you can FOIL, you can distribute, whatever your preference is. But then when you go to combine like terms, I squared is -1. So my final answer is 9 minus 4, which is 5, and then the -6i minus 6i is -12i. Same thing works for number 2. Write it out, multiply times itself. For 3, do not make the mistake of not distributing the negative. It's still a subtraction problem or an addition problem. It does not turn to multiplication. When you distribute the negative, then we would add or subtract to combine like terms. So 1 minus 2 is -1, and then -3i minus 4i is -7i. For number 4, I would distribute the I first so that, excuse me, we get the most simplified exponent. So that's I to the 6th plus I to the 4th, minus I to the 7th. Okay, so to simplify this, I know I to the 4th is 1. Now I'm going to think of the others. I to the 6th has 1 I to the 4th with 2 left over, so that's I squared. And I to the 7th is I to the 4th and I to the 3rd. So that is minus I to the 3rd. I squared is -1. And then I to the 3rd is minus -I. -1 plus 1 is 0. Minus a negative, so the final answer is +I. For 5 and 6, we have complex conjugates that we're going to multiply. So let me write out my work here. I'll box method this one in case you want to see if you want to be a boxer. So we have 5 and 6i. 5 and -6i. So I'm going to multiply 5 times 5, 5 times 6i, -6i times 5, and -6i times 6i. So then that becomes 25 plus 30i minus 30i, and I'm going to do plus 36 because of the I squared. Because we multiplied complex conjugates, the 30i and the -30i are 0, and we are left with a real number of 61. And the same thing happens for number 6. We get 113. So what we're going to do today, if you turn to page 51, we are going to solidify our understanding of addition and multiplication in the complex number system. And we are going to answer on page 51 these always, sometimes, never questions. And here are the directions. If you think the answer is always, you circle always, you're done. You don't have to give any examples. If you think the answer is sometimes, you have to provide one true example and one false example. And if you think the answer is never, you have to provide 2 examples that make the statement false. So I'll do number 1 with you, and then we'll pause the video for you to try 2, 3, and 4. So 1 says the sum of 2 integers is always, sometimes, or never an integer. Okay, so integers are positive and negative whole numbers. So is there any way to add those, because sum is adding, is there any way to add those together and not get an integer? So let's think of some examples. -1 plus -3. Nope, that's an integer. How about 0 plus 5? That's an integer. What about a negative and a positive? What about -2 plus 7? That's an integer. So the answer is always. I cannot think of a time where I add two integers and I don't get an integer. So the sum of two integers is always an integer. So we'll pause the video here. We'll give you about 4 minutes. You try 2, 3, and 4, and then we'll unpause it and check your answers. Okay, for number 2, you should have said always. The sum of two rational numbers is always a rational number. So if we do 1/2 plus, we'll do 3/2, that is 4/2. So even though that's 2 and it's an integer, integers are rational, so that works. There's no combination of rational numbers that you can add and not get another rational. So that's always. For number 3, the answer is sometimes. So for this, we have to provide some examples. So an irrational number, something like the square root of 2, pi, square root of 3. So if I think of the square root of 3 plus pi, that's still irrational. If I do the square root of 3 plus the square root of 2, that's still irrational. Because we're only talking about adding right now. But what if we add a positive and a negative? So root 3 plus negative root 3 is 0. And 0 is not irrational. It is the most specific one you can choose, a whole number. So that is why the answer is sometimes. The sum of two real numbers is always, sometimes, or never a real number. That is going to be always. All right, we've got more to do. Turn the page. On page 52, try the first 9. So try 5 through 9. We'll pause the video. I'll give you about 6 or 7 minutes, and then we will go over the answers. Okay, for number 5, the sum of two complex numbers is always a complex number. The product of two integers is always going to be an integer. And the product of two rational numbers is always going to be rational. So these three, we're talking about multiplication now. Product means multiply. So let's talk about the product of two integers. That's something like 3 times -5. That's still an integer. If I do two negatives, still an integer. If I do, let's do the rationals. If I do, oh, I'm sorry, 5 was sum, not product. We'll get back to the sum in a second. For 7, the product of two rationals, so if I do 1/2 times 3, that's 3 over 2, that's still rational. If I do 1/2 times 1/4, still rational. So back to number 5, sorry about that, that says sum. So of two complex numbers. Well, every number is complex. So, but if I think of 2 plus 3i plus 5 plus 2i. Okay, so that's 7 plus 5i. What if we do 2 plus 3i plus 2 minus 3i? We have complex conjugates. And we add them together, and we are left with 4. But Ms. Weiss, you said they're always a complex number. And that's true because 4 is complex. If you think about the diagram we drew in class the first day, we talked about our number systems, or what they have on page 51. Go back. No, it's not going to let me go back to that. It's okay. I'm not going to be able to turn back. Every number is considered a complex number. So regardless of what answer we get in number 5, it's going to be a number, so therefore it's always complex. Okay, so you've already done 8 and 9. Let me circle my answers for those. For 8, we're going to say sometimes. The product of two irrational numbers is sometimes irrational. So a true statement is something like root 3 times root 2. That's root 6. That's still irrational. But let's say we do root 2 times root 2. Well, that's the square root of 4, which is an integer of 2. Oh, a natural number of 2. So that is a not true statement so for the irrational number. So that is why I chose sometimes for 8. And for 9, the last one you did, always. The product of two complex numbers is always complex, even if it is complex conjugates, like even in the warm-up. And the I term becomes real. That becomes plus 4. So we get 13. Well, 13 is a complex number. Every number is complex. So therefore, 9 is still an always. Okay, you've got 3 more on this page, 10, 11, and 12. We'll pause the video again and give you about 5 or 6 minutes. Okay, so for 10, you should have circled sometimes. The product of two complex numbers is sometimes a real number. Oh, and I used that already in number 9 with my complex conjugates. So if I multiply together complex conjugates, I'll use the same example, and I got 13. That is a real number. But if I multiply non-complex conjugates, let's then do 4 plus I. We're going to get another complex number, not a real number. So even if I simplified this, I would still have this I component. So that's going to be 10 plus 11I. So that is why 10 is sometimes. For 11, the product of two real numbers is always a real number. And for 12, the product of two pure imaginary numbers is always a real number. So pure imaginary is like 3I times 4I. That is 12I squared, which simplifies to negative 12. Or something like I times I, which is I squared, which simplifies to negative 1. So that is why number 12 is always. One more page. Turn to page 53. And we are going to talk about division, quotient. So try numbers 1 and 2 and 3. We'll pause the video and give you about 5 minutes to do them. Okay, so for number 1, the quotient of two integers. So if I divide two integers, I sometimes get an integer. So for example, if I pick integers that divide evenly, I get an integer. But if I even take the reciprocal, it reduces, but that's a rational number, not an integer, so it is sometimes. The quotient of two rationals is always a rational number. Okay, so for number 3, we're going to use the answer to 2. The ratio of the circumference divided by the diameter in a circle is pi. Can the diameter and the circumference both be rational? The answer is no. Look at what we said here, because this is saying these two rationals divide to an irrational. So the reason why not is because one of the measurements is an approximation. So to measure the diameter, that can be exact because it's a linear length. But to measure circumference, you would have to lay a string around the circle and then lay it straight against a ruler or whatever you're measuring that with. So one of them, most likely the circumference, would be an approximation, not an actual rational number. Okay. Your homework is page 55 to 57, numbers 2, 3, 6, 7a, and 11. And you have the remaining time in this period to start that, and we will go over it tomorrow before the quiz.